In this series of videos, I'm designing and building a Z80 based computer system. In the videos so far in this series, I've put together a basic CPU core. I've also put together a video output system, that's a text output, using discrete logic rather than a CRT controller or something like that. And the idea here is to try and build a Z80 system in a very similar way it would have been built when the Z80 processor was first released. That's before all the support chips and large-scale integration devices were available. So I'm making progress. In the previous video I got as far as putting together the control logic for the DRAM, and I showed a single DRAM chip and it appeared to be correctly reading and writing a single bit. And what I've done since then is assembled one of the DRAM boards that I showed previously. It's just a small board that enables me to put all the DRAMs together and saves me having hundreds of these jumpers everywhere. There's hundreds anyway, but it cuts down obviously on the complexity. Also the chances of it working successfully with hundreds of these jumpers flying everywhere is fairly remote, so this just tidies things up a bit. But as you can see, what I've got down here is the small board. It's now hooked in place of the single DRAM chip that I had, and it's also got this resistor pack on the address line. Now I have been asked previously about that and why they were used, and you'll see them on many old designs where there are resistors in the address and sometimes the control lines going to DRAM chips. And they're there for a few reasons. The main one is because you have so many pins all connected together. So all the address lines are connected together, for example. And the problem in doing that is when you then enable those devices, you'll get a large current spike on the address lines. And that can cause signal reflections, it can cause problems on the power rails. It can even damage the devices they're connected to. So by putting in series resistors in the address lines, it dampens out those current spikes and it tends to make the entire system far more reliable. I probably didn't need it with just 8 DRAM chips, but I included it anyway just to be on the safe side. But that's why it's there. It's not. It'll probably work fine without it, but if you have a system that has dozens or tens of DRAM chips, then you really need to include that, otherwise you'll end up with some very odd behavior in the system. So onto this video, and what I've done since the previous video, apart from adding the DRAM board, is I've written a new test program. So the previous one, it was only really intended to test the control logic so I could check the timing signals. It wasn't really intended to check the operation of the memory itself. And the reason it's not very good for doing that is what it was doing is writing to and reading from just a couple of addresses repeatedly, and it was always reading and writing the same value. And the problem doing that when you're trying to test memory is it doesn't really tell you if the value that you're getting back is coming from the correct memory location. It doesn't even tell you if it's coming back from the memory at all. It might just be kind of a ghost value that's left on the data bus, because we're reading and writing so quickly that when the data bus goes into tri-state mode, it will tend to retain the previous value it had for a few nanoseconds. So you might end up just reading the wrong value back. Also, you don't know if you're addressing the correct part of RAM either, because you might always be accessing the same memory location. You'd never know. So what the new test code does, it's still very straightforward, but it's a slight improvement on the previous one. I will keep modifying these to progress the testing, but we have to start somewhere. So as I said, the first test code was to test the logic. This next one is to test start testing the actual RAM. So what this one does is it goes through and writes a unique value to a block of the DRAM. And then when it's finished that, it goes back and it reads all the values back, and if any of the values are wrong, it jumps to a small error loop and just loops around continuously. and we can tell it's gone there even without a logic analyzer by looking at the signals that are being generated by the control logic, because when it's reading and writing we'll see the entire set of signals, the RAS, the CAS, everything else. But when it comes to this loop, it's not reading or writing, or not explicitly reading and writing the DRAM. So the only signal we'll see at this point is the RAS, which is part of the refresh cycle, so all the other signals will stop. So in other words, if we're seeing all the signals, then it's actually working, but if they all disappear apart from the RAS signal, we know that it read back the wrong value, or it wrote the wrong value in the first place. So this is what the test code does. Now the other thing this test that the first test code doesn't is the refresh cycle itself. Because in the first test program we were repeatedly reading and writing the same memory locations in quick succession, so it was doing that every few microseconds, it would have worked fine even without the refresh working at all, because the action of reading and writing the DRAM actually refreshes it. The write, of course, refreshes it because we're writing a new value, but the read also refreshes it as well. That's in fact how the refresh cycle works. So we would never have known with that test if the refresh is working. We could have disabled it completely and the test would have continued working fine, assuming it was working fine to start with. This new test actually tests the refresh to a certain extent. This takes about 6 milliseconds to complete, and that's too long for this particular RAM to retain data in the absence of refresh cycles. Normally the every single address is refreshed probably every 200 or 300 microseconds in normal operations, so it's easily within the couple of milliseconds this particular DRAM needs. But with this new test program, the individual steps are long enough that by the time it gets to this part, it's already outside of the acceptable refresh time for the first memory locations that it's wrote to. So without the refresh, this test would fail. So it's quite a good test. It's testing the fact that we are writing to different memory addresses, because it's writing unique values to each memory address, but it's also allowing long enough for the memory to lose its data if there's no refresh working. So that's what this test will do. Now, a slight correction to the previous video. One of the difficulties in making these videos is trying to keep track of what I'm saying through the video. These can take quite a few hours to put together, and also quite often I'll make a point in the video that unfortunately sometimes I inadvertently edit out, and that's what happened in the previous video. I showed this schematic as being part of the schematic for the logic control for the DRAM, and I was saying that we need to use alternate edges of the 10.8 megahertz clock in order to make this work fast enough to work on slow DRAM. And that's actually true. The problem is this is not the right schematic. This is an earlier schematic that I'd drawn up before I really started fully testing this. It's very similar. The only difference is in this line down here, and also I've got it indicated here that this is connected to refresh, and it is driven through the refresh signal but not directly. So the 2 points just to clarify here are the reason we can't use refresh directly from the CPU. If we get a timing diagram for the Z80, this is the M1 cycle, and the refresh part of it is the T3 and T4 parts of the M1 cycle. And you'll notice at the bottom here we have the refresh line going low, and it stays low throughout the T3 and T4 cycles, and this is the portion of the overall instruction cycle that we should carry out our refresh. This is normally, if there's a read or write operation, it normally occurs after this. But we can't simply drive the RAS signal during a refresh from the refresh signal itself, and the reason for that is because of the way the Z80 is organized internally. And the way it operates as far as this is concerned is at the beginning of the T3 cycle it starts to put the address from the internal refresh counter register onto the lower 7 bits of the address bus. But that takes some time. It's not instantaneous, in the same way it's not instantaneous when it tries to put the address on the address lines at the beginning of the T1 cycle. And that's why the memory request signal doesn't drop until the falling edge of the T1 or the T3 cycles. So although the refresh line drops pretty much immediately at the start of T3, the address on the address pins of the Z80 is not going to be properly stabilized until the falling edge of memory request, and the same is true of the instruction fetch. So that's why we use the memory request and the read line together, or the memory request and the write line together, because we have to do that to make sure that the address is valid. So if we don't use the memory request line in conjunction with refresh, and we just simply latch at the falling edge of the refresh line, chances are, almost certainly, we'll be latching the wrong address into the DRAM, and that means that we'll be refreshing the wrong addresses and the DRAM will lose data. So what we do is we just gate these together, and when they both go low, that's the point at which we lower the RAS signal going to the DRAM. So although on the schematics it looks like we're connected here to refresh, we're not. We're actually gating the refresh line by the time it gets here with the memory request line. I'll show the schematic for that in a later video. The other correction is down here. As I say, we're using alternate edges, and this is the correct schematic. And the only thing that's really different here is the clock to the second flip-flop is connected to the input of this inverter, not the output. If you connect it to the output, it will still work for fast DRAM, but we're kind of running out of time if we do this, because we're always using the rising edges of the clock. So we're always using the rising edge here or the rising edge here, and that adds about 100 nanoseconds to the overall time for the cycle. I'll just demonstrate that now. This memory I've got in here is fairly fast and it's new as well, so it tends to operate fine. And so I'll start this running, just power it up, and you can see on the scope hopefully that we're getting some signals that are, I'm hoping, fairly clear. What I'm going to do is move the camera so you can see these a bit more clearly. So what we're looking at here on the screen is the purple line is the RAS signal falling at the beginning of the cycle, and if we put the cursor halfway down there, we use the kind of midpoint of the slopes, and the yellow line is the write line going to the DRAM, and if we put the second cursor on there, we're getting about 14 nanoseconds. So in other words, the write line is dropping about 14 nanoseconds after the RAS line, which is fine. That gives the DRAM plenty of time to prepare itself. If we then move the cursor line to the blue line, that's the multiplexer. So the lower part of the address is latched into the DRAM when the purple RAS line drops, but then we have to wait a short time and then change the multiplexer. And I don't know if you can read it, but we're now about 90 nanoseconds after the falling edge of the RAS signal, which again is plenty of time. The memory, according to the spec sheet, it needs sort of between 60 and 70 nanoseconds between these two, and 90 gives us a bit of overhead, so that's fine. If we then move on to the green line, that's the the CAS signal. And again, we have to wait a while after the rising edge of the multiplexer, because the multiplexer rising edge is where the multiplexer switches to the high order address bits. And we're now at 176 nanoseconds. And that's, we're getting on 200 nanoseconds for the duration of this signal. If we switch to the other cursor line and we go up to where the yellow signal starts to rise, that's the point at which the cycle is over, and beyond that it's too late for the memory to do anything. So in this case it's showing 142 nanoseconds between the falling edge of the CAS signal and the rising edge of the write. So it's on the limit of what the memory will tolerate if it's 150 nanosecond memory. Obviously we should be no more, or rather no less than 150 nanoseconds. This is actually working. I'll explain why we know it's working in a few minutes. But what I'm going to do now is just quickly change the schematic so that instead of it being wired like this, it's going to be wired like this. As I said, the only difference is the clock line going to the second flip-flop is going to the input of the inverter, so we're using alternating edges of the 10.8 megahertz clock. So I'll power this off. I'll move the jumper so it's now in the correct place. Power this back up. So you can probably see the difference already. I'll move the cursor lines back so we can test the timing again. So put the first one on the falling edge of the RAS signal, and then the falling edge of write should be in the same place, 14 nanoseconds, that's where it was before. The rising edge of the multiplexer should be where it was previously, so it's about 80 nanoseconds or so. And then if we switch to the other line and we look at the falling edge of the CAS, if you remember, this was about 100 nanoseconds after the rising edge of the multiplexer. It's now at about 30 nanoseconds, and the memory only needs about probably 10 or 15 nanoseconds at that point. So again, we have some overhead there, but more importantly, if we now see how much overhead we have on the memory timing, we had, if you recall, about 140 nanoseconds. We're now at 206, so we're now allowing 206 nanoseconds for the memory to do its thing, which is more than enough for 150 nanosecond DRAM. Okay, so the reason that we know this is working is because the write, the CAS and the multiplexer lines only toggle if we are actively trying to access the DRAM. So I'll move the camera back so you can see a bit more of what's going on. So at the moment we're running this test program. It's loading up the memory block with unique values. It's going back, reading them each in turn, and if it detects any problems it will jump through to this loop here. And as long as it's going through this block and this block, we'll see all the signals on the scope that we're currently seeing. However, if it jumps through to an error, so if it detects an error, if it reads back an incorrect value, it'll jump here, then all it does, it just loops around. So the writing and the reading will stop. However, the RAS signal, if we've got this right, should carry on because the refresh should continue. The Z80 will continue with its refresh cycle because the M1 cycle is of course still running anyway. But we're just not explicitly trying to read and write the DRAM. So if we force it to the error loop, we should see all the signals apart from the purple ones stop. So I'm just going to pull out one of the jumpers. So the jumpers on the right here are the data lines going to the DRAM. If I pull one out, obviously it's going to read back the wrong value, so we should jump through to the error part of the program. So I'll pull one out, and you can see fairly quickly it's jumped through to the error and all the data, all the logic activity has stopped apart from the purple one. It's not synchronized with purple, which is why it looks like a mess. But if we single shot that, you'll see that there is activity on that line. And that is the refresh cycle, but everything else has stopped. If we reset the processor, then the test program starts up and we're successfully reading and writing to the DRAM. So we'll start up the logic analyzer, have a look at how it appears on there, and hopefully we can prove that this memory system is in fact working. I've got the logic analyzer up and running, and I've got the trigger set to address 4000 FE hex. and because we're writing to a block of code starting at 4000, the block will end at 4000 FF, so we'll end or will trigger just before we get to the end of this block of code, which is where it's loading the memory up. And the bit we're interested in is of course reading it back. So we'll arm the analyzer, see if it actually triggers. The Z80 is running at this point. So the analyzer has indeed triggered, and we should now be just before the end of this block of code. And if we now start scrolling through the analyzer display, we should get through to the second block where we're starting to read the values back from the DRAM. And the instruction we're particularly interested in is the one at 13 hex, which is the address where we read back the value from the DRAM, and we compare it with the value that's currently in the A register. And if they're the same, then the test passes. If they don't match, then the code jumps through to the error loop. So what we should see is incremental values starting from address 4000 each time we get to the ROM address 13 hex. So we'll start scrolling through. And so we've now got to the first instance of address 13 hex, so we've just got through to this point in the code. The instruction there should be BE, which as you can see it is. And if we keep scrolling through, we'll see it trying to read a value from the DRAM, and the value starts, the way this test works is it starts at a data value of 0 and it counts up by 1 each time. So 4000 should have a value of 0, 4001 should have a value of 1, 4002 value of 2, etc. So we'll go and look at the second loop. So we're looking for it to come back round to address 13. This is address 13, and this time we should see a value of 1 coming back from the DRAM from address 4001. You can also see the addresses down here. And again, notice that the second part of the address is inverted. If you recall, part of the address bus is inverted because of the way the logic works, but it doesn't really matter because we always invert it, so we're always reading and writing the correct addresses. Okay, we'll go around again, have a look at the next address, and 13's come round again, and sure enough 4002 has got a value of 2. We'll look at one more. And this time 4003 has a value of 3. Again, we know these are correct because I can see on the scope that the test is still running, and if it makes or detects an error, then it will stop. So I'll just move the camera back down. So as you can see, making good progress. We've got the logic sorted out for reading and writing to a DRAM. It's working reliably. I'd actually left this test running for about 4 hours earlier and it ran fine. I came back, it was still running. It won't recover if it finds an error, it will just permanently stay in the error loop. So even with this arrangement of having all these jumpers flying everywhere, it's reliable. You can see that the signals are very stable. There's no jitter, there's no kind of rogues or runt pulses anywhere, and that's exactly what we want to see. We don't want to see the edges bouncing back and forth because that will indicate that we have some timing issues somewhere. And the fact it runs without detecting errors for hours at a time means that we're probably not borderline with anything. Certainly the timing that we're measuring would seem to indicate that we have about 50 nanoseconds, at least 50 nanoseconds spare in the memory access. And again, we're looking at the write cycle here, which is worst case. So it's looking promising as far as this is concerned. So the next thing to do in this project is to start designing some memory mapping. At the moment I've just divided the memory into 2 chunks. The lower chunk's for the ROM, the upper chunk is for the DRAM. But we will end up with something a bit more complex than that. We're going to have two banks. One bank will have the ROM, the in-out memory mapped area, and then we'll have some common RAM and some video RAM, and in the first bank we'll have the main bulk DRAM. So we'll look at that in the next video, but as you can see, we are now making some progress.